So similar with the last video, we learned a lot of different concepts and we went through a lot of different problems in Units 4 and Unit 5, which were on radical and quadratic functions. I'm not going to go through all of those notes, all of those concepts. Rather, I want to kind of point you guys in the right directions for where I prefer you guys focus your studying. And then we'll go through some problems that are aligned to what you can expect to see on the final. Lesson 4.03 is on graphing radicals. That is definitely one concept I want you guys to know for this. Kind of making a table using the right x values to graph a radical function. I go through a problem like that in today's video, and then it's on the homework for the week as well. Additionally, lesson 4.08, advanced radical equations. So these are radical equations that have two radicals where you have to isolate the one radical term, square it, do a little bit of algebra to isolate the other radical term, square it again to solve for x. So that is another area of focus. And then lastly, you're going to see this come up in other units as well, but I can't stress enough the importance of transformations. That's a major theme that you guys have seen this year, and you're definitely going to see it come up on the final exam. So I'm not going to go through notes because we've had quite a few notes. Rather, this is just where I want you guys to focus when it comes to content from Unit 4 and Unit 5 that will be aligned to the final exam. Okay, so let's start by going through problem set 1, which is going to cover algebraic type questions, and then we'll go into graphical questions like we did last video. Okay, problem set 1. So we're going to go through two questions here. One is going to be covering radical functions, and then the second one is going to be covering quadratic functions. The first question, we want to solve the following quadratic functions, or radical functions, radical functions. So here we have a radical equation written down, and we want to solve this for x. Okay? So the idea here is we're going to isolate the radical term, which is this right here. To do that, in this case, we're going to subtract 6 on both sides. And now we're going to square both sides to undo the square root. On the left-hand side, when we square a square root, those operations cancel each other out. We're just left with x plus 3. And then on the right-hand side, negative 3 times negative 3 is positive 9. And so what we get when we solve this algebraically is x equals 6. However, when we're covering radical functions, there are sometimes situations where the solution that arises when we solve for an equation algebraically is not actually the solution. So we always want to make sure we check our work and see if this solution is actually a solution. Okay? Let's plug in 6 into this equation. I'm going to put a question mark up here. And now let's simplify the left-hand side. So we have the square root of 9 plus 6 equals question mark 3. 3 plus 6 equals 3. Well, 9 does not equal 3. So what that means is the only solution that we got when solving for this algebraically is not actually a solution. So we'd say this question has no solution. And then to be a little bit more particular, x equals 6, we call this an extraneous solution. An extraneous solution. Okay, let's do one that's a little bit more challenging. Okay, so over here, let's go through letter B. which is the square root of 3x minus 8 plus 1 is equal to the square root of x plus 5. Okay. What we want to do when we have two radicals is we want to isolate one of the radicals. Once we isolate one of the radicals, we can square both sides. So right off the bat, we've isolated the radical on the right-hand side. So let's square both sides. The right-hand side will be pretty straightforward because the square and the square root will just cancel each other out. What I want to do on the left-hand side is write this twice. And then the right-hand side is just going to stay. The operations cancel, and so we're just left with a radicand. So now let's FOIL the left-hand side. When we multiply the square root of 3x minus 8 by itself, it's really just kind of squaring it. And so we end up with 3x minus 8. That's this right here. And now we're going to multiply 3x minus 8 by 1, and then add to it 1 times 3x minus 8. Well, that's plus 2 times the square root of 3x minus 8. And then lastly, we're going to take 1 and multiply it by 1. So we're left with this. Okay, now let's isolate the radical term by doing a little bit of algebra. So the 1 and the negative 8 on the left-hand side can combine together, and we get negative 7. The right-hand side will stay the same. Let's bring these terms over, these non-radical terms to the other side. So I'm going to subtract 3x, this is negative 2x, and then add 7 plus 12. Okay, now we can divide by 2. So negative x plus 6. Now we're going to square both sides again. And this will get rid of the square root. So 3x minus 8 is equal to negative x plus 6 times negative x plus 6. So the left-hand side is going to stay the same. Now let's FOIL the right-hand side. This becomes positive x squared minus x times 6. So this is minus 6x minus another 6x. Well, that's minus 12x. And then lastly, plus 36. Okay, let's subtract 3 and add 8. So we get 0 is equal to x squared minus 15x plus 44. Okay, so we want to think two numbers that multiply to 44 but add to negative 15. This one's a little bit trickier, but it is factorable. We end up with x minus 4 times x minus 11. Okay, and I'll save a little bit of time by not plugging these back in on this video, but I would encourage you to plug these values back in to check to see if they are extraneous. And what you'll find is this solution is extraneous, whereas this value, x equals 4, is the actual solution, because when you plug it back in, the equation works out. Okay, so the x equals 4 is the answer to number 1, letter B. And we're going to wrap up the video by going, wrap up this problem set, sorry, not the video, by going through number 2. So we want to demonstrate that this function here has complex solutions. Okay, so to determine that, we're going to set this equal to 0. There's a lot of different ways we can solve this, but based on how it's written already, it's in vertex form. What I'm going to do is, let's avoid using the quadratic formula in factoring if we can. So I'm going to subtract 7 on both sides. Now let's divide by 2. And then we're going to take the square root of both sides. So we end up with plus or minus, let's write it in terms of the imaginary number I. Plus or minus I times the square root of 7 over 2. And now let's add 2 on both sides. Okay, so these are complex solutions because there isn't an imaginary part. Okay, so we've answered, or we've verified that the solutions to this are complex. What would we do to transform this function up here so that the solutions aren't complex? Well, if the function is complex, that means the function does not cross the x-axis. So imagine we have this function here. I'll just draw a little sketch. The vertex is 2, 7, so it looks something like this, maybe. Think about what transformations you could make to this function so that it crosses the x-axis. There are a good amount of answers that we could have that would work. So just kind of think to yourself what transformations we could undergo to this function so that it crosses that x-axis. I'll just go through one example, but there's a lot of different ways you can approach the last part of this question, letter B. Let's move it down. I'll move it down 14 units. So we're going to go down, shift down 14. Okay. And what that will do to the function is instead of having plus 7, it's going to be minus 7. So now we have this new transformed function. And what I would like to do is let's just prove that the solutions are real solutions. Okay. So instead of subtracting 7, now we're going to add 7. Now let's divide by 2. Now we're going to take the square root. So remember, plus or minus square root of 7 over 2. Positive 7 over 2 now, not negative 7 over 2. Sorry, we already did this. And now we're going to add 2 on both sides. So 2 plus or minus square root of 7 over 2. And we've verified that our transformation that we've done will give us real solutions rather than the complex solutions. So these are real solutions. Okay. So now let's take these concepts and let's apply it to more graphical questions in problem set 2. So for problem set 2, we're going to go through graphing and analyzing the graphs for radical functions for number 1 and quadratic functions for number 2. So here we have a radical function for number 1. Let's start by first rewriting the function over here, and then I want to give the general form of a transformed radical function. So here's our radical function. The general form that we've seen before is a square root of x minus h plus k. And the starting point is always defined as h comma k. It's similar to the vertex of a quadratic function. And in this case, for this specific example, this is going to be equal to positive 3 comma 1. So that's letter A. What we want to do for letters B and C is we're going to create a table that has some select points that we can use to draw a graph of what this will look like. Okay, so the table. The tricky part about the table with radical functions is we want to pick x values that give perfect squares underneath the square root. So we already have the starting point, that's 3 comma 1. So think to yourself, what numbers could I plug in here so I get a perfect square underneath the radical? Perfect squares are the numbers like 0, 1, 4, 9, And what I mean by perfect squares is when you take the square root of those numbers, you get an integer rather than some irrational number. So we plug in 3, we get 0 underneath the radical, so that one works out nicely. Another one we could use is 4. If we plug 4 into the radical, we get 2 square root of 4 minus 3 plus 1. Well, that is just 2 times 1 plus 1, which is 3. And then another one we can use is the number 7. 2 times the square root of 7 minus 3 plus 1. 7 minus 3 underneath the radical is equal to 4. The square root of 4 is 2, times 2 is 4, plus 1 is 5. And so the y value when x equals 7 is 5. Okay. That, I think, is enough. Those are enough points to draw a reasonably accurate graph of what this function is going to look like. Okay, so x equals 3 when y equals 1, so that's a point here. X equals 4, y equals 3, right here. And then 7, 1, 2, 3, 4, 5, 6, 7, goes up to 5. So the graph will look something like this. It's going to start here. This is our starting point. And then it's going to go off like this. These graphs are parabolas on their side cut in half. That's the shape that these make. And the domain does not exist over here to the left of the starting point. So the graph has no y value over to the left of x equals 3. Okay, to wrap up question 1, let's talk about what the transformations are. Transformations are a big part of the curriculum that we've learned this year. We've seen them in every unit pretty much. So for letter D, let's say we have g of x equals the square root of x, and then f of x, which is the function we were just dealing with, is 2 square root of x minus h plus k. Sorry, instead of h and k, we're going to use 3 and 1. Okay, so let's state the transformations. Well, inside the radical, the minus 3 indicates that we're shifted right 3 units. Outside of the radical, the 2 indicates that we are there's a vertical stretch by factor 2. And then lastly, the 1 on the very outside it's shifted up 1 unit. Okay, and so those are the transformations that this function f of x has undergone from the original function square root of x. All right, and to wrap up the video, let's go through number 2. So we want to give the equation in vertex form, in standard form, given the graph here, and then we want to demonstrate algebraically that this has complex solutions. Remember, because this graph does not cross the x-axis, the solutions for it will be complex, so we have to prove that algebraically. The general form of the vertex form of a quadratic function is written here. We know that the vertex of the quadratic function is h comma k, and so the vertex in this problem is 3 comma 2. And so what we can do here is plug in 3 for h and 2 for k into this function. Now we need to solve for a. The way we're going to do that is we're going to use a coordinate point on the graph, plug this coordinate point in for x and y, and then use that to solve for a. So let's pick 1 comma 6. So 6, the value of the function, is equal to a times the value of x, which is 1 minus 3 squared plus 2. So this is our x value, our coordinate point. This is our y value. This becomes 6 equals a times negative 2 squared plus 2. Well, we could subtract 2 on both sides, so we get 4 is equal to 4 times a, and so a is equal to the number 1. Which means that the function written in vertex form that represents this graph over here on the left is equal to x minus 3 squared plus 2. Okay, so that's the function in vertex form. Now we also want to write it in standard form. So this is x minus 6x plus 9 plus 2. I just expanded that and FOILed it. And so the function written in standard form, ax squared plus bx plus c, is this right here. Okay? So that's this. All right, then lastly, what we're going to do is just prove that this has complex solutions. We know that it has to have complex solutions because the graph doesn't cross the x-axis. We have this little gap right here. And so what we're going to do is set this function equal to 0 and prove that the solutions to this equation here are not real numbers. Okay? I think it's easier if we use the function in vertex form. It'll make the algebra a little bit easier. So what I'm going to do is subtract 2 on both sides. Now we're going to take the square root. So we have plus or minus the square root of negative 2. Well, plus or minus the square root of negative 2, that's plus or minus 2 times I, the imaginary number I. And so the solution to this equation is a complex number. And it is a complex number because the graph does not cross the x-axis. Okay, so it's really important that you guys know that for the final exam. Okay, to wrap up the lesson for today, work through the additional practice here on the OneNote. So these are more application questions. Okay, so you'll need a calculator for these, but once you finish this video, move on to this additional practice on the OneNote.